Hey everyone, and welcome. Today, we're going to talk about the smart shortcuts that pretty much run our digital world. We're diving into heuristics, those clever, good enough solutions that power everything from your GPS to the future of AI. And we'll even look at the massive challenges that still lie ahead for algorithms. All right, let's get into it. So let me start with a question for you. What do your GPS and a chess grandmaster actually have in common? I know, it sounds kind of weird, right? One is just a piece of tech calculating routes, and the other is a human mind making these incredible intuitive leaps. But believe it or not, the answer connects them both, and it's the absolute key to solving some of the toughest problems in computing. But before we get there, let's just quickly set the stage. Algorithms, they're the invisible architects of our modern lives. At their core, they're just sequences of steps used to solve a problem. They're what helps you search for that one perfect thing online. They sort all that information so it actually makes sense. They schedule things like traffic flow to keep our cities moving. And they transform data so our devices can even talk to each other. They really do make an impossibly complex world manageable. But here's the thing. Not all problems are created equal. Some are just so massive, with so many possible combinations, that even our fastest supercomputers would totally fail. We're talking about problems where checking every single possibility, the brute force approach, would take billions of years. In computer science, this special class of super tough problems is known as NP-hard, and they really are the final frontier of what we can compute. So if we can't just throw more processing power at these absolute monster problems, what do? How do we find the shortest route through 1,000 different cities, or figure out how a complex protein folds if the perfect answer is literally out of reach? Well, the answer is we cheat, but in a very, very smart way. We use heuristics. See, a heuristic isn't about finding the single perfect answer. It's about finding a good enough answer and finding it right now. It's an educated guess, a rule of thumb, basically an intelligent shortcut that trades that absolute perfection for speed and just being practical. And that's the strategy that both your GPS and that chess grandmaster rely on. To really see how this works, let's make it a little more concrete. Just imagine a robot trying to navigate a maze. It needs to get from point A to point B as efficiently as it can, avoiding walls and obstacles. This is a classic pathfinding problem. A really popular algorithm for this is called A-star. Now, the genius of A-star is that it doesn't just blindly explore every single possible path. That would take forever. Instead, it intelligently prioritizes the paths that seem the most promising, the ones that look like they're heading in the right direction. But how does it know which path is promising? It all comes down to this pretty simple formula. The total cost of any path, which we'll call f of n, is just two things added together. First is g of n, which is the actual distance the robot has already traveled. That's a known fact. And the second part is h of n, which is the estimated guess of how far it is from its current spot to the finish line. And that estimate, that is the crucial part. Right, so how does it make that guess? I mean, if the estimate is too complicated to figure out, the whole algorithm will be slow. But if it's a bad guess, the algorithm might just go down the complete wrong path. The quality of this estimate, this h of n part, is literally everything. You guessed it, it uses a heuristic. One of the most common ones for a grid, like our maze, is called the Manhattan distance. And it's just beautifully simple. It completely ignores diagonals and any obstacles in the way, and just calculates the distance like you're walking on a city grid. How many blocks over plus how many blocks up. So it's not the actual distance the robot will end up traveling, but it's a fantastic, super fast, good enough estimate. This is a perfect illustration of how a simple heuristic can guide a complex algorithm to a quick and really useful solution. So we know heuristics help us solve incredibly complex problems, but what about the ones that are still tantalizingly out of our reach? Let's take a look at the algorithmic frontier, at a class of famously hard problems. One of these huge challenges is calculating the edit distance between two strings of text. Now, this might sound simple, but it's actually the cornerstone of everything from spell checkers and search engines all the way to computational biology, where scientists are comparing massive sequences of DNA. Take these two words, for example, Saturday and Sunday. I mean, we can intuitively see they're pretty similar, but how do you actually quantify that for a computer? How many little steps would it take to transform Saturday into Sunday? The answer is 3. Using a common measure called the Levenshtein distance, the edit distance is 3. It takes a minimum of 3 simple changes to get from one to the other. So here's one way you could do it. You delete the A, then you delete the T, and finally, you substitute the R for an N. Boom, 3 steps. Now that's easy enough for us to trace with short words. But just imagine doing this with 2 strands of DNA, each millions of characters long. All of a sudden, the number of possible ways to transform one to the other, it doesn't just grow, it explodes exponentially. That is what makes it an NP-hard problem. And here's the crucial part. This problem is just one of a whole class of related, monumentally difficult problems. The incredible thing is, if someone, somewhere, finds an efficient, perfect solution for just one of these NP-complete problems, it could be the traveling salesman problem or the knapsack problem, they will have found a key that solves all of them at once. It would be one of the single greatest breakthroughs in the history of computing. And that brings us to our final thought. You know, modern AI and machine learning are, in a lot of ways, the masters of heuristics. They don't solve problems with brute force logic, they learn patterns and they develop their own good enough strategies to make predictions and decisions. So the question to leave you with is this: will one of these heuristic-driven AIs, a good enough machine, eventually become so good that it discovers the perfect key to unlock these perfectly unsolvable problems for us? Thanks so much for joining us for this explainer. If you found this useful, we'd really appreciate it if you'd like, share, and subscribe for more deep dives into the technologies that are shaping our future. We'll see you next time.